Okay guys, this one is lecture 26, which was not covered by section 3 and 4, starting from the slide 24. Starting off with the cis fatty acids. So fatty acids by definition are long chain carboxylic acids that have got two main sources. They are found in vegetable oils and they will be known as unsaturated fats there, and the animal fat which mainly provide the saturated fats. These fatty acids mainly constitute the fats and they are monomer units of most of the fats that we find in nature. So they have got two sources, vegetable oils and animals. Vegetable oils usually have unsaturated fats in them, means they have got double bonds in it, whereas the animal fats they usually have the saturated fats, mean no double bond in it. Kindly make one correction in this one. For the spellings, this one is animal fat and not fat, so cut this E out of it. And the example shown here is oleic acid, and this one is the cis variety. As we can see, this is the carbon-carbon double bond found in oleic acid. It's only got one double bond, and both the hydrogens are on the same side, therefore this is the cis variety. And do remember that this oleic acid, the cis form, is found in olive oil that we usually use for cooking, and is usually found in every house. Now some trans fatty acids also exist but they don't have any natural source, so no natural source for these trans fatty acids. But there is a way by which we can convert the cis fatty acids into the trans fatty acid. So in that diagram is shown the same oleic acid but the trans form. So we can see the carbon-carbon double bond and hydrogen are on the opposite side. One is above the bond and one is below the bond. That's why this one is called the trans oleic acid. So as I said, there is no natural source for them. And when we expose the cis fatty acids at very high degree temperatures for a long period of time, then those cis fatty acids are converted into trans fatty acids. And do remember that these trans fatty acids have been reported to lower the levels of HDL cholesterol, which is considered to be the good fat in the body, and they elevate the bad LDL cholesterol, which is considered to be the bad fat in the body. So in other words, these trans fatty acids have got a double dangerous effect on the body. They lower HDL, which is a good fat, and they increase the LDL, which is the bad fat. And both of these factors will contribute to cardiovascular diseases and can result in the heart failures or the myocardial infarctions, because these bad LDL cholesterol can get stuck in blood vessels and can cause atherosclerosis. Next slide is about the alkenes in nature. So these alkenes are abundantly found in nature. In plenty of things that we observe in nature, these alkenes are present. One important use of the ethene, which is the simplest of these alkenes, composed of two carbons, ripens the fruits. So they help ripening of the fruit. The fruit grows and becomes ripened fairly quickly with the help of ethene. Then there are polyenes built from the isoprene skeleton, and the structure shown here at the bottom is isoprene. Can be important for exam purposes. The diagram can be there and you can be asked what structure it is. It is known as isoprene. So these polyenes or isoprenes can join together to make these big structures known as polyenes or isoprenoids. So this one isoprene is considered, you can say, monomer unit. Many of these can join together to give us polyenes. Means many of these isoprenes join together make big structures. So these isoprenes or isoprenoids are found in nature abundantly. One such example is geraniol, and this one is found in roses and in geraniums, which are other species of the plant. So usually found in the plants, especially in the roses, geraniol. And another of these isoprenes is limonene, which is found in oil of lemon and orange fruits. So these are two examples for the isoprenoid. More examples of isoprenoids found in nature. Another one is myrcene, which is found in oil of bayberry, and this is the plant of bayberry shown in the diagram. And another one which is particularly important is farnesol, found in the lily of the valley, and on the right is the diagram of the plant lily of the valley, and from that we can extract this farnesol isoprenoid. Next are reactions involving alkenes and alkynes, and the key reactions of these alkenes and alkynes are addition reactions. We saw basic classification of the reactions. Addition reaction were when two molecules combine to give a new molecule. Such reactions are called addition reactions. So they are the key reaction that involves these alkenes and alkynes. Which type of additions are there? One is hydrogenation, and as the name suggests, it is going to be the addition of hydrogen atoms. Second is halogenation. Again, common sense, addition of halogen atoms will be called halogenation. The third one is hydration. Hydra is a word usually used for water. So these are addition of the water molecule. And the last one, hydrohalogenation, in which a hydrogen halide molecule will be added. That means one hydrogen and one halogen joined together. The compound is called hydrogen halide, so that will be added up to the alkenes or alkynes in hydrohalogenation. So addition as a general reaction is shown in the diagram. So an alkene is there with a double bond between the two carbons right here, and it is going to add up a molecule AB. So how this addition usually works is, this is a small molecule AB that reacts with the double bond that is present between the two carbons. The double bond will break and its electron will be used to bond to the A and B pieces. So this double bond will be broken and converted into single bond, as we can see here in the product side, and A will be added to one carbon and B will be added to the other carbon. So they make two bonds over there. Sometimes these additions require a catalyst. A catalyst is a molecule that speeds up the chemical reaction, so makes the reaction faster. So some of these reactions are very slow to happen. So in order to fasten them up, we have to add a catalyst to the reaction. Here is another way of classifying these addition reactions and the different types. One type is known as symmetrical reactions, and these addition reactions are the ones in which same atom is added to each carbon. So both the carbons take up the same atom, and the examples are hydrogenation, in which there will be addition of the hydrogen molecule or hydrogen gas. So one of these H will go to one carbon and the other H goes to the other one. Another example is halogenation, which also exists in diatomic form, like bromine, chlorine, both exist in Br2 and Cl2 form, which is the diatomic. So one Br goes to one carbon and the other one goes to other, and therefore same atom is added to this to each carbon, so they will be called symmetrical addition reactions. Second variety is unsymmetrical, and in these ones hydrogen and another atom are added to two carbons. So one carbon will take up hydrogen, the other carbon will take up some other atom. Examples are hydrohalogenation, and these hydrogen halides like HCl or HBr, these will be added to the alkenes. One carbon will take up hydrogen, the other will take the halogen. In this case can be chlorine, bromine, fluorine, and so on. Second type of unsymmetrical reactions are hydration reactions. and these will be adding up the H2O molecule. Again, one carbon will take the hydrogen or H positive, the other one will take the hydroxyl ion. And this hydration reactions is a difficult reaction, very slow reaction, and it requires a strong catalyst. So this point is important to remember. A strong acid catalyst has to be there for this reaction to work. Third variety of these addition reactions are self-addition. And in these reactions, the molecules, many of the same molecules, basically many of the same alkenes or alkynes will join together with each other to make a big molecule, which is known as polymer. So such reactions are also called as polymerization reactions. So hydrogenation shown in a little bit of detail, which is the addition of the hydrogen gas or H2 molecule to the alkene or alkyne. So an alkene is shown with two carbons and hydrogen is added up. As I said, one hydrogen bonds to one carbon and the second hydrogen bonds to the second carbon. So this will result in an alkane because the double bond is broken and two hydrogens will be added up. The remaining the product formed at the end will be known as alkane, and the double bond, same things are repeated here. Double bond is broken, new carbon hydrogen bonds will result. And platinum, palladium or nickel, these are the three catalysts that are used. So one of these will be mostly used or has to be there, and these catalysts are usually written at the top of the arrow to tell what is the catalyst for that reaction. Heat or pressure can also, may also be required at times. So again, these are slow reactions. We need some catalyst, we need some heat or pressure for these to get going a little faster. Hydrogenation is also a reduction reaction basically. So in this diagram, a cyclohexene is shown with a methyl group. So 2-methyl cyclohexene is adding up the hydrogen. Same basic thing that occurs in other hydrogenations. One of the carbons around the double bond will take one hydrogen, the second one will take the other hydrogen, and this double bond will be broken. So we can see a single bond only remaining here, and two hydrogens have been added up. Platinum or carbon are the catalyst for this reaction. So it is usually done with the help of metal catalyst, and the catalyst is necessary most of the time for hydrogenations because this HH bond is very strong and it is not easy to break that bond, and we have to break it in order to add each hydrogen atom to each carbon. So these are a few steps how this hydrogenation occurs in the laboratory. First up, the absorption of hydrogen on the metal surface happens. So this hydrogen is absorbed on the metal surface. Then the alkene will approach the surface, and this addition is strictly called the SYN or syn addition. Both hydrogen will come from one side. So both of these hydrogens are going to come or add up from one side, and such an addition is called syn addition. More examples of syn addition. So another cyclic structure is shown adding up to hydrogens, and the main thing to remember about the syn addition is the two hydrogens. As we can see, both are represented by dotted bonds, therefore they are both coming from the same side of the plane or the same direction, and that is a property of syn addition. Second one is also a similar structure, dimethyl cyclohexene, and it is also adding up the hydrogen, and it is also an example of the syn addition where both the hydrogens are added from the same site basically. Next up is halogenation, which is the addition of a halogen molecule represented by the X2 here. So we have got an alkene, and in place of the hydrogen it's simply a halogen X2 molecule. Same thing will happen, the double bond will break. One carbon will bond with one atom of X and the other one will bond with the other atom of X as shown in the product side, and the product formed is known as alkyl dihalide this time, that has got two halogen atoms in it. So same steps which I just said are mentioned here. Double bonds broken, new CX bond will be formed. Two of these will be the result. And this reaction, very important thing to remember this point, that it occurs quite readily without a catalyst. Hydrogenation, we saw, almost always requires a catalyst, but this one is a ready or spontaneous reaction, so it does not require a catalyst. And the chlorine and bromine are the halogens that are most often added up. So the halogenation reaction is shown how to do it in the laboratory. This one is a bromination of an alkene. So the left side beaker, which has got orange color, is the one that has bromine only. No hydrocarbon is added, or no alkene is present in that one. Now with the help of this apparatus, when we add up the alkene in that beaker, what happened is the color changed from orange to transparent. So color change happened, which shows us that the reaction has occurred or with the hydrocarbon or with the alkene. So this results in colorless solution. Another example of halogenation reaction. So this time we have got a tube butene made up of 4 carbons and a double bond in the center, adding up the chlorine halogen. So one chlorine will go to this carbon of the double bond, and the other one goes to the other carbon. The double bond will be broken, and this will result in a single bond, we can see, and each of the carbons that were involved in the double bond takes up the chlorine molecule. A typical example of halogenation. Next up is the reaction that is known as hydrohalogenation. And in hydrohalogenation, we add up the hydrogen halide, which is represented by this HX. This hydrogen halide has got one hydrogen and one halide, which can be chlorine, bromine, any of the halogens. So in general represented by the X. So more or less the same concept that was there in hydrogenation, that was there in halogenation, will apply here as well in hydrohalogenation. So this is an alkene, and the actual example with ethene made up of 2 carbons and 4 hydrogens, and the hydrogen halide used in this case is hydrogen bromide. So the same thing that happened in earlier reactions, the carbon double bond will break. One carbon takes up the hydrogen and the other carbon takes up the bromine, and the result will be bromomethane, or in general we call it alkyl halide, that has got alkyl group plus a halogen atom in it. So reaction, this one also occurs quite readily without a catalyst. So these reactions do not need a catalyst as well, just like halogenations, but hydrogenation do require a catalyst most of the time. Next up is also hydrohalogenation, but for the unsymmetrical alkenes. Means the bigger alkenes basically that have got 3 or more carbons, just like the propene shown here. Now the basic concept is the same, that we are going to add up the hydrogen halide. One carbon of the double bond will take the hydrogen, and the other carbon will take the bromine. But the problem is that we have got 2 options in this case, that the hydrogen can go to the central carbon, or the bromine can go to the central carbon. And this will result in 2 products, or 2 possible products basically. In one of the products, the bromine attached to the carbon number 2 here, and the minor product, which is 1 bromopropane. In this one, the bromine is attached to carbon number 1. So there are 2 possibilities in such reactions when hydrohalogenation occurs with the unsymmetrical alkenes. Now the question is which carbon will take the bromine and which carbon will take the hydrogen. So in this regard, we have a scientist here, Markovnikov, which developed a rule after some experiments, and this rule is on the next page. So let's move on. So the Markovnikov's rule states that it was a Russian scientist. Not really need to remember. Anyways, so he did plenty of experiment on these double bonded carbon systems, and he noticed that the majority of the times hydrogen went to the specific end. Now, which end did it go most of the time is formulation, and which is at the bottom. So hydrogen most often goes to the carbon of the double bond which had more hydrogens attached in it. So before the reaction, the carbon which had more hydrogen will take up the hydrogen, and the carbon which had less hydrogens will take up the halide or the halogen atom. So looking at this example will help us understand a little bit better. So this is an unsymmetrical alkene to which the hydrogen halide has to be added. In this case, it is the HBr. So the double bond will break as usual. One carbon is going to take hydrogen, and with one carbon is going to take bromine. So the Markovnikov's rule stated that the hydrogen will go to the carbon with more hydrogens. So if we look at these two carbons, this carbon in the center has no hydrogen attached to it, whereas the one on the left has got two hydrogens already. So this one has got more hydrogen. So the incoming hydrogen will go to the carbon which has more hydrogens already present, or the carbon with more hydrogens mentioned here. And the bromine or the halogen will go to the other atom most of the time. The two possibilities still exist, but these are usually calculated in percentages. So you can say like 80 or 90% of the time this Markovnikov's rule will apply, and the hydrogen goes to the leftmost carbon, and this will be the result, the product on the right side. So the hydrogen is added to the carbon which already had more hydrogens, and the other carbon takes up the bromine basically. So you can say this product will be there maybe 80% or 90% of the times, and the remaining 20% of the time the opposite can happen as well. It has the possibility to happen. So a couple of more examples applying that Markovnikov's rule. So again we have got a butene with the double bond present between carbon 1 and 2. HBr, hydrogen bromide, is added. Acetic acid is the environment in which this will happen. So as we discussed, now in this case the carbon on the right side or the rightmost has got two hydrogens, which is this one on the right side. This one has got two hydrogens already present, whereas this one we can see only has one hydrogen. So according to the Markovnikov's rule, this hydrogen will go to the carbon that has got more hydrogens most of the time, as I said. So when this happens, this will be the product form. Hydrogen went to the rightmost carbon, and the halogen went to the other carbon, which was this one, and this will result in this product, and this will happen 80% of the time. The remaining 20%, the opposite can happen as well. Same thing for the second reaction as well. So in this case, the left carbon has got no hydrogen in it. So this is the one with fewer hydrogens, and this one we can see has got two hydrogens attached. So according to Markovnikov's rule, the hydrogen will go to this carbon, and the bromine atom will go to the left carbon, and this will result in the product which is shown here. And this will happen, as I said earlier as well, 90% of the time. The remaining 10% opposite will happen. A couple of more examples for the hydrohalogenation. So this is the cyclopentane and hydrogen chlorine. Hydrogen chloride is the hydrogen halide that is going to be added to this one, and the carbon-carbon double bond. So the two carbons that are present here, not shown, we have to assume them. The double bond is broken. One takes up the hydrogen, and the other one takes up the chlorine, and the result will be chlorocyclopentane in this case. Similarly, methyl cyclopentane, and again it will be an example of hydrohalogenation, adding up the hydrogen fluoride to this cyclic structure.